Okay, finally I can see me here today.
Okay.
Yeah, I just have to just figure out the lighting, but yeah, you can see.
Yeah, no, that's fine. Okay, so yeah, hopefully others will turn on in some time. Okay, so we are at JPA. So the first presentation was titled JPA a deep dive. This time it's JPA a deeper dive. Okay, so let's start. Um, so I will start from the very basics so that everybody can just understand what's going on. So what is self-supervised learning? Self-supervised learning is an approach where a model learns useful representations from unlabeled data by creating its own supervision signals. Or you can say an approach to representation learning where the system learns to capture the relationships between its inputs. So it is learning the pattern in the data. So that is what self-supervised learning is because you don't have any labels. So you're creating your own labels. So what are the types of self-supervised learning? Um, there can be two types. It's one of the ways to do that. So there is invariance-based methods and generative methods. And just to uh, make the terminology constant for the rest of the presentation, when I say X, that is the augmented and corrupted part, and Y, that is the original part. Okay, so first let's look at what invariance-based methods are and what do I mean by invariance-based methods and generative methods. So in generative methods, you would have seen these things like BERT masked language models and stuff. So you are given an input X with some corrupted part of the input, and you want to learn to predict the corrupted content completely. You are just completely predicting that whatever has been corrupted, you have to go from the corrupted X to the Y. So the strength of this type of method is that it requires less prior knowledge, but the weakness is that the resulting representations have a lower semantic level and underperform on off-shelf evaluations. So if you were to train it on something and then test it on a different distribution or distribution as in different data set having a different distribution, it will underperform a method that has been trained with invariance methods. So what are invariance methods? So invariance methods are optimized to make similar embeddings of different views. If we are talking in sense of an image, so different views of the same image. So if you have some kind of this kind of a structure in the network, it's from Dino. There was a paper called Dino, and its full form is self-distillation with no labels. This just wanted to let you know. So you have in the X part of it, you feed some kind of a corrupted input, and why you have the original input going in, and then when it reaches the end of the network, that's the Y cap. The loss is calculated in Y cap. So Y cap is the representation space. It's not actually going from X to completely to Y. It's doing the loss calculation and everything in the representation space. So it is actually abstracting away a lot of these unnecessary details that you don't need to predict actually to understand what that data is. So these are invariance-based methods. The strength of them that they can produce representations of a high semantic level because they have eliminated that the unnecessary details. So if there is an image, there can be a lot of values of pixels that you can change minutely and get almost the exact same image again, right? So to get that high semantic level of representation, this is invariance-based methods perform a lot better than generative methods in that sense. So there is one weakness, but that's not really not really a weakness that comes up a lot. That is that the augmentations and different kind of uh, the corruptions that you will use, that can introduce strong biases that can be detrimental for certain downstream tasks. So you have to choose your augmentations that you provide in X carefully, so that they may not be so uh, it'd be better for the downstream tasks, not perform worse on them. So, is this clear? Do you have any questions? You can stop me anytime and ask me again, and I'll try to explain it again. So, if you have any questions, please just stop me anywhere. Okay, so I think nobody has a question. Okay, let's move on. So, now let's come to the problem with self-supervised learning. What is the problem when we were looking at these kind of methods and different these two different kind of methods that we looked at? So the problem is, it's called the uncertainty problem. So this is a typical task given to a machine learning model. So imagine that you have to fill the masked part of the signal or the image, and this masked part can be filled in the representation space in invariant space methods, or it could be in generative methods. You'll have to completely fill it, right? So the loss will be calculated against the original signal, and this is the task that you have been given. Like, how can you fill this black box inside of this? So you've just masked out a part of the signal. Now the thing is, like, how can you possibly fill this gap in between? What can be done? So these different representations that you see, like different ways to connect these two signals, these are all valid and these are good approximations, and all of this is acceptable in a self-supervised learning. When you are doing self-supervised learning, you don't have any labels, you're just trying to learn the signal itself. So all of these are good representations, good approximations. But when you are doing, let's say, a generative method, you'll be constructing that entire signal again. But and essentially what you will be doing is trying to memorize the data itself instead of understanding it. So because all of these different approximations are also good, they are not bad. So all of these approximations should also be learned by the model, but it doesn't happen because you have that certain bias inside your model, that you have to exactly reconstruct what you were given. In invariant space methods also, when you don't have when you are predicting in the representation space also, you are still predicting the exact representation of the y of the y network. Is this clear? Is this clear? Okay. So so the thing is that the set of y compatible with a given x may be a single point, that you can connect the two signals by just one. If it was small enough, you could just draw a straight line that could be just a single point, or it could be, there can be multiple discrete points, or a manifold, or a collection of points and a manifold, right? So there can be different ways to connect to fill that masked part of the signal. Or in images, you can think about filling the masked part of the image. So there can be different ways to do this. So there is a lot of uncertainty how to do this. And when you are training the model with invariance methods and generative methods, you are not really getting the model to understand the data. So that is what we are trying to encode. We are trying to encode all possible variations of data into a model's parameters, biasing it to learn the data instead of understanding the data. So this is exactly what's happening in autoencoders, BERT, and LLMs, and Dino, in this Dino architecture. So what this leads to is a poor actual generalization, and these methods become very data hungry because they are actually ingesting a lot of data. And this may be one of the reasons why scaling laws have been working so far, as the model is ingesting and storing the data and its parameters and biasing it to properties of data which are actually unpredictable, right? You cannot actually predict these things. So now let's so that is why we should not impose that the model be able to predict original x from the corrupted x, right? So it may be difficult or intractable to explicitly represent the set of plausible predictions, but it is more convenient to ask the system to tell us if a proposed y is compatible with a given x. We just want to know if the y that we have, is it compatible with the given x or not. This is where looking at models as energy based models comes in handy. So let's first look at what exactly are energy based models. So an energy based model defines a scalar energy function. It's like there is a function called e that takes in two inputs, x and y, and the training objective is to learn parameters of the function e theta, the theta, such that the compatible x, that is y plus x and y plus, if they are compatible, their energy should be less, and if they're incompatible, their energy should be high. So if you see in this diagram, the dotted line, the dotted line is what you want, that it is the x is compatible with y. So that is the dotted line, and that's why the energy landscape is shifting in a way so that it becomes lower energy in region, everything else becomes higher energy. Okay, so is this clear? Because this is a lot to take in, I know, because we are going to move into a lot of these details. So if you have any questions, please stop and ask me. If you want me to explain anything again, please ask me.
Just one question on my part. Like I'm not familiar with JEPA, so this is a good explanation. One question I have is like in the traditional models, like they uh, calculate loss between prediction and the actual signal, and then we minimize the loss. So here also in the visuals, like it looks like we are minimizing some sort of loss. So what's the difference between the energy function and the loss functions that we traditionally use?
Yeah, so in the traditional functions, traditional loss functions, what you are doing is, uh, so for example, you are in let's say you are doing some form of generative architecture kind of a thing, or you are doing just a predictive, just a simple prediction, also a simple prediction, a regression problem or classification problem. In that you have a loss function which is just looking at one point and seeing if that one point is compatible with another point and not. It's not about making an energy landscape and how that point behaves with everything else around there. I think it will be more clear to you once I'm ahead in the presentation, where I will show you different architectures and how they behave. That will be much more clearer. So, okay, anybody else?
Um,
Anybody else wants to say
I
anything?
just, yeah, I just had a question.
Hmm.
Like, for till now, we have, this is essentially how all models have worked. Like, we have a true point and we have a prediction, and
Yep.
we try and compare it. Generative case, you would compare the actual value, and in the um, other case, the invariant case, you would compare representations, correct? So, I mean, this has been working so far, right? I mean, the main issue I see with it is that it's data hunting. Is that the point that we are trying to highlight? That
So,
because this approach, it's been working, right? Because any model, the majority of them, other than the energy-based ones, we trained with this approach. There is a loss function that you try to minimize. That loss is computed over a true value versus a predicted value.
Yeah, so
So I'm
there are two
curious.
things. So there are two things.
Yeah.
Yeah. So I understand what you mean. So there are two things. Generative methods, these are like constructing X back from a network, and you are compressing that like an autoencoder and coming back out to generate an X again. That is a generative method. A simple predictive is just a normal regression problem and a classification problem. Is that what you're talking about? The regression and classification problem? A simple network that can just do some kind of a regression or classification task.
I mean, you're, if I'm trying to understand, I'm just trying to grasp the intuition behind what you have said.
Yep.
Like, we have a true value, we have a predictor, right? Whether it's regression, whether it's classification, that is the case, right?
Hmm.
And generally, we operate by minimizing the loss between these two entities, right?
Yeah, but that comes under supervised learning.
But in self-supervised learning also, like,
Yeah.
you're trying to minimize the distance, right?
Yep.
I mean, I'm not able to grasp the intuition because it sounds to me like you're saying that this approach has issues with it. So what I'm trying to grasp is that what that issue is. Is it the fact that it's data hungry?
So it's,
Like
yeah, it's not just data hungry. So if you, so in this example, like this is how you train in self-supervised learning, right? You mask a part of the signal, or you mask a part of the image, or you mask something, and then tell the model to fill this thing. So the problem here is that in generative architectures, in any other kind of architectures, you are just telling the model to fill this thing with just one thing. So when you fill this with just tell the model, okay, this is the y and this is the x, and can you fill this in between and get this comparable to y in some sense. So the model actually learns the original thing, but there are different ways to connect the same thing, right? Different ways to, in images, if you blank out the, let's say, the eye part of a face, there can be different ways to just reconstruct the eye part. There could be like 10 eyelashes, 15 eyelashes, 20 eyelashes, or there can be a lot of different solutions to the same thing.
But
And
you're fundamentally changing the assumption then. Like, so far, the underlying assumption has been that there is one ground,
yeah, yeah, there is,
right?
so when you are doing self-supervised learning, you are trying to learn the representation of data. You're not trying to
Right.
to have some supervised thing there, that okay,
Mhm.
this is x, this is an x that maps to a y. So
Mhm.
because in self-supervised learning, you're trying to understand what that data means in a representation space. Once you have that representation, you can do all sorts of cool things with it. Just even just a normal classification task on top of that representation space will work a lot better because you have a good
Okay,
vector
so
representation.
you're coming at this from the point of view of how we can generate a better representation. So from
Yeah,
that point of view, you don't want the model to just learn the original signal, but rather you want it to be able to grasp neighboring representations as well.
yeah,
Is
it
that the
should, yeah,
objective?
it should. If you have a good enough representation, every other task is simplified. And so if you do supervised learning, the problem with that is that it is limited to the data that you have in your hand. So the data in supervised learning needs to cover everything that is out there in the world. So it actually is learning in a supervised fashion to just map x to y. It can work. It's not that it doesn't work. We have seen that it does work.
Yeah.
But in self-supervised learning, we are telling the model to learn by itself without any supervision. So it can actually understand the patterns inside of the data.
So we don't want to confine it to just what we deem as the ground truth.
Exactly.
But in certain applications, there would be just one ground truth, right?
Yeah. So once you have trained with self-supervised learning,
So that
You
would
can
be
do
the
that.
problem in the downstream task.
Yeah,
So,
that would be a downstream task problem. So you have a good
right.
representation, and after the good representation, you have a linear layer or a non-linear probe attached to it, or you're doing a
Exactly.
full fine-tuning after that. So it becomes more uh, a better way to
Yeah.
uh, classify or
Yeah.
do regression things.
Yeah. A richer representation that would possibly generalize. Like, I'm guessing that would be the goal.
Yeah. So this is where when uh, certain AI people talk about world models come in, because world models would need to understand the entire thing itself.
Yeah.
Okay.
So I would like to add one more thing. Thanks for the good discussion. So I'm also not 100% sure about the intuition, but then I watched a video lecture by Yann LeCun who proposed this, and he says like some things that make case for this energy-based models. Like he says, uh, we people learn in a different way. Like if you don't know car driving, like somebody can take maybe 10 or 15 one-hour classes, and then at the end of that, they'll be able to drive a car. But if you try to teach these current deep learning models, millions and millions of hours of driving data, even after that, like it's not as good as someone 18-year-old person with 15 hours of training. And also he says like there are some zero shot learning tasks. Like you can ask a 10-year-old kid to like stack the dishwasher. And even though he has never done that before, he may be able to do it because he has understanding about the world. So these kind of learnings are not possible with the current model. So he makes a case for this. I'll share that. Maybe I can try to find that
Yeah,
video and
exactly,
share it.
exactly. This, this
Yeah,
this was a great point. Yeah, this was what this was what was needed for the discussion. Thank you.
yeah. And based on the discussion, like so here, previously we were trying to just learn the data, whatever is the original, we try to predict. So here we are trying to understand the class of original functions that would be a best fit for the current perfect one, right? Like something like that we are trying to do.
Yeah, it's something like that.
Okay. We'll have like multiple solutions for a problem, like because we are approximating, and at the end we'll like as she said, if we have only one class or like particular classes, so that will collide to that particular solution. Is it the
Yeah.
way?
So so right now we are trying to understand the problems.
Mm.
So and now then we'll move on to why JPA was created and how it comes from and how it can be used to solve these problems.
Okay, perfect. Yeah.
Okay. Anybody else want to say anything? Add anything? It's a good discussion. Okay. So where were we? I think we were on this slide. Wait, this one. Yeah, so energy-based models. Everybody's clear on that? Okay. So how would an energy-based model look like if we were to draw it? So it's just like there are two inputs going into an energy function, x and y. Y could be a y plus or y minus. Y plus would mean that it is compatible with x. Y minus would mean that it is incompatible with that with x. So it's just a notation that I'm clarifying. Okay, but this is all good. But how do you enable a model to represent multiple predictions? How can it represent multiple predictions? So that is where latent variables come in. So handling uncertainty with latent variables. So a latent variable can be seen as parameterizing the set of possible relationships between x and y. Okay, I'm just saying right now. I know you don't understand it because I also didn't get it the first time. So latent variables are used to represent information about y that cannot be extracted from x, right? So just like uh, in the signal which we had masked out, we don't know how we could connect those 2 points of the signal. There can be many ways to do that. So latent variables are used to represent that information. So in a okay, so in a temporal prediction scenario, the latent variable represents what cannot be predicted about the future solely from X and past observations. Okay. And okay, for example, if you are driving a car right here. So if you're driving a car, you are this red dot, and there is a yellow. There's a car in front of you that is represented by this yellow dot, and you are coming on a fork. So in the future, if you're trying to predict something in the future, you won't be able to predict. You won't be able to know where the yellow car will go. Will it take a left turn or a right turn? But if you use a latent variable, you can represent these options inside of that latent variable. So imagine that you are sitting in the car and seeing that the car is the car in front of you. So you will be like you can internally represent the options in your head. So you'll be internally representing, okay, so this car will either go left or right. So these are two options that you've represented inside your head. So that is like a latent variable. So latent variable can represent these options. Okay, is that clear? Is that clear?
Yeah.
Okay. So why is this not moving forward? Yeah, okay. So a latent variable energy-based model is an energy function that depends on X, Y, and Z. So Z is the latent variable here. So when presented with a pair X and Y, the inference procedure of the EBM finds a value of the latent variable Z that minimizes the energy. So in the inference procedure itself, what you are doing is you are minimizing the energy function with the constant X and Y for Z. So so as you can see in this equation, that you are first you are minimizing the energy function over Z to get the exact output of the energy function. So there's a minimization problem inside of the energy function. Is that okay?
So this happens during inference, not during training, is it?
Yeah, this is happening in inference. Just give me a second.
Sure.
Yeah, this is happening in inference. So there is a minimization problem in inference. Is everybody okay with that? I know it can be a bit hard to grasp. Is everybody okay with that? Can we move forward? Or if you want me to explain it again, I will do that. Hmm. Okay, let's move forward.
Sorry. Can you explain it again? So, what is this concept of X and Y? Is X the input, Y is the output? And if Y
So
is the output, if is Y plus Y minus like a binary
yeah,
classification
okay,
term?
okay. Let's move back to the
Okay.
this slide. So whenever I'm saying X and Y, this is what I mean. So X is the augmented or corrupted input, and Y is the original, what we are sending to the network.
Y is the original input.
Yeah, it's the original. So it's a self-supervised learning. So you're
Oh,
sending
okay. Got it.
exactly the same thing.
Yeah. Okay. Okay.
Okay, so but when we are talking about energy-based models, it can be any X and Y. So in terms of self-supervised learning, we know that X will be some corrupted form of it, and Y would be the original thing.
Okay. Got it.
Okay, everybody's clear on that? Okay.
Yeah.
So now coming to, but okay, this is this. Oh wait, we have done this, right? We have done this. Uh, okay, yeah, this was done.
Mm.
So now let's come to training energy-based models. How do you train these models? So the objective is pretty clear. What we need to do in energy-based models, that is, we need to make the energy of compatible inputs lesser than the energy of incompatible inputs. That is X and Y minus incompatible, and X and Y plus are compatible. So making the energy of a training sample low, that is X and Y plus, is very easy. Like you just give some augmented part of and let's take an example of an image. If you have an image, you just mask out some part of it, and there is another the original part of it goes through Y, and the normal corrupted parts goes through the other part, and then you have these two things that are compatible, and this then just you compute some kind of a loss, maybe an L2 loss or some kind of a loss, and it's pretty easy to do that, right? It is just you know what two inputs are compatible because you already have X, and you can just corrupt it in some way and get that Y plus out of it, right? But the difficult question is, how do you ensure that the energies of all Y minus that can be present are higher than Y plus? Okay. That is the difficult question. So, without a specific provision to ensure the objective for all Y minus, the energy landscape can suffer a collapse. Let me read that again. Without a specific provision to ensure the objective for all Y minus, the energy landscape can suffer a collapse. Okay. So, what is a collapse? What is a collapse? Let's come to what do I mean by collapse? Because there are two meanings of collapse, and you might be so. There are two types of collapses that can happen. One is called neural collapse. The other is called representation collapse. So what I'm talking about right now is representation collapse. That is the bad collapse. But there is also neural collapse, which is a good collapse. So, and let me just read out the definition, because neural collapse is in itself a whole other topic, and I will not go deep into that. I'll just read out the definition for you. So, neural collapse is a phenomenon observed in the late stages of training a network. That is the terminal phase of training a network in classification tasks. So, it refers to certain simplification in the structure of the learned representation and the classifier's weights that occurs as training progresses. Okay, so the convergence of certain patterns in the feature space of the neural network as they approach the optimal solution during training. So it's like the different classes are being clustered together in one representation. So that is a form of neural collapse. So if in a representation space, if all of the same classes get mapped to a single point, that is a neural collapse, because that is a good representation. Every member of a certain class get maps to one single point. That is a good representation. They have different classes, and we have a classification problem on our hands. So that is a good collapse. That's a neural collapse. And the other thing, that is representation collapse. That is what we are talking about right now. So,
So one question. So,
yeah.
So the neural collapse is something desirable. So the JEPA model is trying to do something like that, right? Like represent the class of functions that minimize the energy to a single uh, value or like single point.
No, so neural collapse is a good collapse. It's just I just wanted to give you an idea about what do I mean by collapse, because there is another word out there that's called neural collapse. And while hearing that, you might think that it is a bad thing, but it is actually a good thing,
Mm.
and which actually represents generalization of a model. So if it generalizes, neural collapse does happen a lot of times. So I think the paper that I sent Aditi, I sent you the paper. It talks about that neural collapse problem, and
Mm.
how it emerges when you have a good generalization.
Yeah, yeah.
Okay. Just give me a second, guys. I need to put my laptop on charge. Okay, so any other questions? No questions, okay.
No,
You have a question?
no, all good.
Okay. Okay, now coming to representation collapse. So collapse happens when a model learns embeddings where all inputs look the same. So what you will be doing in minimizing the loss in a energy-based model or any model, you'll be minimizing a loss function. So let's assume that your loss function is just L2 loss, and L2 loss would be just comparing to two embeddings that you're getting out of. So let's say, okay, in this you have an input right here, and one augmented part goes here, the other original thing goes here, and then you have these two embeddings, and you're calculating a loss on top of that. So info NSE loss is a very common loss that is used in contrastive learning. We'll look at what contrastive learning is. So this is a loss that is being used. So there will be a comparison of two embeddings using some L2 norm, and that will look like this. And so if the model, just imagine if the model learns the same representation for all of the input that you're giving it, all of different inputs that you're giving it. So the loss will get minimized because the distance between these two embeddings will be zero because they are exactly the same. But they won't actually mean anything because the representation has collapsed to a single point. You cannot distinguish between two different kinds of point if they are all mapped to a single representation point in the representation space, right? So so there was this paper, Understanding Dimensional Collapse in Contrastive SSL. If you look at this paper, you will see how they have theoretically proven that in contrastive SSL, this kind of a collapse happens if you're using strong augmentation and implicit regularization. So this just wanted to put that out there. This happens in contrastive SSL with strong augmentations and implicit regularization, but it can happen in other architectures also, not just contrastive based methods can happen, but in contrastive methods, it's because of strong augmentation and implicit regularization. Okay, cool. Let's move forward. Okay, so yeah, one more thing. Implicit regularization means, what does that actually mean? It means when you are using layers like batch norm, dropout, which inherently cause the network to be regularized instead of adding some regularization term in it in the loss function. Okay, yeah. Now, okay, so what EBM architectures are susceptible to collapse? Okay, so the thing that you were talking about, I think somebody mentioned it. So in a normal prediction scenario, let's say this is just a prediction regression network, the A part of it, this one. So there will be no collapse in that. Why? Why there will be no collapse in that? You're doing the exact same thing. There is an X goes to an encoder and then a predictor, and then you are comparing directly the Y part of it. Right? So why won't there be any collapse in this case? The collapse in this case, there won't be a collapse because you're not converting Y to anything. So it's like one X is being mapped to one Y. It's directly one to one mapping. There is no multiple mappings out there in this case because there is no different kind of augmentations to figure out and different things to fill in. So it's because there is a single Y and you're producing it from X, there can be not there can be no collapse. Okay. But if you are using a generative latent variable architecture, there can be a collapse. If you're using an autoencoder type of a thing, there can be a collapse. And if you're using a joint embedding architecture, which looks like this, if you see right here, if you're using something like this, there can be a collapse. So if you want me to go through like why does these collapse happen, we can also do that. But Okay. I'll just tell you in one line. So, in generative latent variable architecture, if you give the latent variable a lot of informational capacity, it will collapse because then yeah, I don't want to get into the because of it, but just because I want to move forward. So, this
Mm-hmm.
happens because of the high informational capacity of Z. And in autoencoder, if um, the latent space is very large, it can happen there too because the latent space is very large. So in the latent in the autoencoder, when there is a bottleneck that you have in between, which you use as the representation, if that is very large, equal to the original size of X, or even larger than that, there can be a collapse that can happen because it can learn just a one-to-one mapping there instead of running the representation itself. So there can be a collapse that can happen. And in joint embedding architectures, it's the same thing. If the both of the encoders learn to exactly map the same point to same thing, it's the exact same thing that we discussed before. Okay, is everybody clear on this?
Yeah, I think because the latent variable are representation of the data itself, is it because of the reason like the collapse is happening because we have the information we are putting and also the latent information. So at the end of the point, like they are representing the same
So
point.
yeah,
Mm-hmm.
for the models that have latent variables,
Mm-hmm.
the thing is, if that latent variable has a lot of informational capacity, what
Mm-hmm.
it will do is it will actually learn the actually like
Bias.
memorize the data
Bias.
instead of getting representations from the X encoder. The latent variable will actually contain everything about the Y part of it. So it
Mm-hmm.
will learn that mapping through latent encoder, and there will be no use of X
Mm-hmm.
encoder at all.
Mm-hmm. Okay,
So
rather
your
than
encoder
generalization.
will not work.
Mm-hmm. Okay. It will not generalize, right? This is the point.
Yeah, it won't generalize
Okay.
because everything will collapse. Everything will
Okay.
get
Yeah.
mapped to one point, or
Mm.
it will just go haywire.
Got it.
Okay, is everybody following me up till now? Okay. Okay, let's move forward. Okay, so now the thing is, how do you prevent representation collapse in energy-based models? So again, what our objective is, it is clear. This is the equation that we need to enforce. So the question now becomes, how do we design loss function to prevent collapse? So the whole thing about all of these different uh, papers coming out and all is to create a loss function such that it can prevent collapse. Create a loss function, do different kinds of uh, cool tricks and some kind of different things to get the model to not collapse. So there are two approaches to this thing. To prevent collapse, there are two approaches that you can take. One is contrastive methods, the other is regularized methods. Okay. So just to give you an overview, what contrastive methods are and what are regularized methods. So in contrastive methods, what happens is that for the points that are compatible with each other, for let's say this is the representation space and all of these dots are compatible with each other, we want all of these dots to have a low energy. So in contrastive method, what you will do is pull all of these points down in the energy landscape, and you'll generate contrastive samples, these green points right there, and try to pull them up. So the energy becomes higher for these contrastive samples and lower for the compatible samples. Okay, this is the overview of contrastive methods. And in regularized methods, what you're trying to do is just minimize the volume of the low energy space, you're trying to minimize the volume of the low energy space, and also you're trying to just the simple thing of getting the compatible inputs energy low and trying to minimize that volume. You're trying to do that in regularized methods. So now just let's look at what contrastive methods are from a little bit more theoretical point of view. So in contrastive methods, what we want to do is to create a loss function whose minimization has the effect of pushing down the energies of compatible points and pulling up the energies of suitably hallucinated contrastive samples. So what do I mean by suitably hallucinated? That just means that you're generating contrastive samples in some way. So that is suitable hallucinations. So the loss that you create here would be directly proportional to the compatible inputs. That the uh, I think I think I think I messed up. So this is the energy. So energy should be directly proportional to, wait, am I saying this wrong? Yeah, compatible inputs energy should decrease. So it's a loss. So loss of the compatible input should decrease, and the for the incompatible inputs, it should increase. There should be a increasing, decreasing kind of a function there. So if you look at the examples of contrastive methods that are out there, you can see that there is maximum likelihood, or GANs, or denoising autoencoders, masked autoencoders, or even SimClear. So some people might have gone through SimClear. So that's an example of contrastive methods. But let's come to the problem with contrastive methods. So the problem with contrastive methods is that the first is that you have to create a scheme to generate suitable contrastive samples. You have to create a scheme. That is a hassle of creating a scheme out of you are just given a data set, right? You're just given a data, and get us to create a scheme to generate suitable contrastive samples, you it's a bit hard task, because you might introduce some kind of a bias in there, right? Because of your different contrastive samples, if they work or they don't work, there could be different biases that can come from there. That is one thing. The other thing, that is the main part of the contrastive method, that there is a curse of dimensionality. So in the worst case, the required number of contrastive samples may grow exponentially with the dimension of the representation. So just let's see in this image again. So in the contrastive samples, you need, just look at this image, like you need a lot of samples just to pull the entire energy space up, right? So as your dimensionality increases in the representation space, you'll need a lot more samples to get the energy of all the different y minus out there. And to increase their energy, it will take you a lot of samples. So if you are reading if you're going through code of somebody who's used contrastive learning, or going through some paper, you will see that when they are using a representation space, their representation space would be very small, because of this, because they want to have a constricted representation space, so that they don't have to generate as many contrastive samples. Okay, are we clear on this? So this is why we should avoid using contrastive methods. That is where regularized methods come in. So in regularized methods, we construct a loss function that has the effect of pushing down on the energies of compatible samples and simultaneously minimizing the volume of y space, which to which the model associates a low energy. So in equation terms, the loss is directly proportional to xy plus and the volume of y plus. Okay. So the example is PCA, k-means clustering, sparse autoencoders, variational autoencoders, VQVAs. These are the regularized methods that are out there. And just to mention it, contrastive and regularized methods are not incompatible with each other, that is, you can use both together, but I don't think you need to. I don't think you will need to. So the question now becomes, how can we design such a volume minimizing regularizer? Because we already know, yeah, x and y, minimizing x and y plus, it's easy. But how do you get a regularization term that can minimize the volume of y plus, right?
I have just one question.
Yeah.
Sorry for interrupting. So, previously we saw for contrastive methods, like we need to hallucinate contrasting samples, right? Like
Mhm.
generally, the data set will contain both the positive and negative examples, right? So, in such cases, like why can't we use negative samples as contrastive points? So, in that case, like
Yeah,
we don't
I
need to.
know, I know it can get a bit confusing. So remember, we have to remember that we are doing self-supervised learning. So there are
Hmm.
no labels.
Okay, okay.
There are no
Sorry,
labels.
yeah, my
Yeah,
bad.
yeah, positive and
Okay.
negative. It's just not there. Okay.
I had a question.
hmm
What is the advantage of trying to minimize the volume?
So, so when you are actually minimizing the volume, um, right here. So when you are trying to actually minimize the volume, so what would happen if you don't minimize the volume? If you, let's say you have a sheet of paper, sheet of rubber, and you're trying to pull this down. And when you pull this down, there will be a huge shift towards this. There will be a lot of energy. So if this is an energy landscape, a lot of energies will become lower for that. So with a restricted volume, what you would have is something like a very sharp dip. And that is actually good for your model because this is what the data has shown it, that this is the only thing that works. Everything else is higher.
Okay,
Does
so
it make
like if we
sense?
don't constrain the landscape, there is a possibility that we might accidentally minimize the energy of some of the incompatible samples as well.
Exactly.
So that's why we want to restrict it so that we only minimize. Because I think in one of the slides you had mentioned that we want to get uh, the energy of all the incompatible samples up for like every single incompatible sample.
hmm
Or was it the other way around?
Yeah, that was the contrastive methods where you're pulling everything up, everything else up, and the compatible ones down. That's what you're doing in contrastive methods.
And here we want to still pull like the compatible samples to a low energy
Yeah,
space, but also constrict like the volume, which in turn ensures that the energies of all the compatible samples would go up.
incompatible would go up.
Incompatible, yes,
Yeah,
correct.
exactly.
Yes, okay, makes sense.
Okay. Anybody else has a question? Okay. Let me get to where I was. Yeah, I think, yeah, I think we were here. Now, okay, just to give you an overview of the scene architectures, what we have already seen, because now we'll be coming to JPA. So what we have already seen, a joint embedding architecture, where you have an X encoder and a Y encoder, and they are both just processing X and Y, and you're calculating loss in the representation space. That's one. And the generative architecture where you have an X encoder and a decoder, and that can have a latent variable, and then you have the decoder get the Y out of it, right? So this is the two architectures that we have seen. Now, coming to JPA. Uh, Come on, move. Yes. Okay. So in joint embedding predictive architecture. So JPA is joint embedding predictive architecture. So JPA comes from what we have learned so far. So we want to learn a good representation to understand the data. And for that, we will need latent variables to address the uncertainty problem. So that is one of the motivations behind it. And the part that we don't want to generate the exact thing, like do the exact thing what generative models are doing. Why we don't want to do that is because there can be a lot of different things that can be represented there, right? There will be a lot of different ways to represent the same image. There can be different pixel values. A little bit change of a pixel value doesn't entirely change the image, right? So that is why we don't want to go to generative part. We are trying to constrict that to a representation space so that it becomes more abstract. So it becomes more semantically meaningful. So that is why we come to joint embedding predictive architecture. So it's just like a joint embedding architecture with a predictive component over it. So this whole architecture, the JPA architecture with both of these encoders and everything, will be an energy-based model. The whole thing would be an energy-based model. So the energy is simply the prediction error in the representation space. So it is simply the energy. So how you can see this is, if you have so the first part is to calculate the z. If you remember, the inference procedure is to first minimize z. So to minimize z, what you do is you give the energy function x and y and z, and you minimize this energy function over z. So and there is an argmin of z, and then there is, so in JPA, what you have, there is a predictor that takes in z and the representation that you have extracted from the X encoder and a Y encoder. I will show you then an image that will make it much more clearer. And then after you have calculated this, you have minimized this, you have a Z bar. That is the optimal Z. And then you come to finally calculating the energy of that. Uh, that would be just the distance between d is the distance between sy, the prediction of y, and the predictor network with sx and z bar. Okay, so let's look at the architecture of it so that it becomes much more clearer, because equations are heavy. So right here, so if you have if there is an x, there is a y. So x goes through the x encoder and then a predictor which also has a latent variable z, and then y goes through a y encoder. You have this should be an x. So yeah, this should be an x cap, sx cap, and sy. So you are calculating the loss right here. Then the loss would be the distance function d s over sy cap and sy. Let's call it sy cap. Okay, sy cap and sy. So this is, so the procedure of going from here to here is a bit complicated. It's not just straightforward that you are just doing a forward pass. So because of you have to minimize for z, this predictor network has to have, because z starts from here, you have to have a minimization right here, minimization steps right here. So you can have a, let's say, gradient descent working on just this part of the network with a constant x and y to minimize z, to get a minimum, to minimize the energy function with regards to z. So when you get that, then you have the actual sy cap value, and then you calculate the distance. And after you have calculated this distance, then you do your training procedure, whatever is that is, like you want to do back propagation or anything. Okay, so this is how JPA forward pass works in a JPA. So now there are two ways a JPA may represent the multiplicity of values of y compatible with x. One is the invariance properties through y encoder. Y encoder can have some invariance properties, and the latent variable z. There are two things. So just a second. So what have I written? Okay. So yeah, so in this way, when you are using, because you're using multiplicity of values of y with compatible x, you are essentially eliminating the uncertainty problem, because all of that uncertain behavior, like what different values could be there of the signal, get pushed to z, to the latent variable. All of these options are represented in z. And when you are minimizing over that, you are just searching for which is the optimal solution there. And all of that is fine, because the model itself that you will be using as representation, that would be this part, that would be the x encoder. Finally, you will be taking out the x encoder and using that for representations. That is free of that uncertainty, because the uncertainty gets pushed to z now. Is that fine? Everybody fine with that?
I'm not so sure about like Z.
Can you just go back just one slide to
Okay.
equations?
Yep. You want me to tell you anything? You want
Yeah,
me
I
to
just
repeat
want
it
to
again?
clarify the second equation.
Okay. So fxy is your final energy
Okay.
that you get.
Mm-hmm.
That is the final energy that you will get between x and y.
Mm-hmm.
That is the minimization over z of the energy function EW, that is parameterized by W,
Yeah.
x, which takes the input x, y, and z.
Mm-hmm.
So when you are minimizing over z, this is the equation for that,
Yeah.
right? And then after you minimize this for z, this is what you get. There's a distance. You'll be calculating a distance d between sy and the output of the predictor network. The
Okay.
predictor network takes in xx and z bar. Z bar is the optimal value of z.
Okay. So there is a comparison between the SY and the output which we are getting from the X encoder and the
Yeah,
late
yeah.
variable.
So this
Okay.
is sy,
Mm-hmm. Got
this
it.
is the sy part, and this is what you're getting out of the predictor.
Okay. Okay. Fair enough.
Okay.
Yeah. Thank you.
Hmm. Okay. So there, what was your question? Can you please repeat it again?
Um, like you said, we are minimizing Z,
Mm-hmm.
and once you've minimized Z, then that goes to the predictor, and that's what the second equation does.
Yeah.
Right? So I'm still not very clear on like what
I can tell you what I understand from he was saying. So there are three variables, like we want to like minimize the distance between whatever prediction we get from our input and also the output in the latent space. And so we have a variable that we can control called z. So let's say like your finally the sy hat and sy is the representation, like latent space representation of the output, and sy hat is the latent space representation of the predicted output. So you want them to be as close as possible in whatever the distance that you are calculating. Let's say there are two vectors like this, and there is another lever that you can control called z. And when you change z, this you are not going to change the latent space representation of the output, but by changing z, you can change the latent space representation of the predicted output sy hat. So it can move based on the z. So you try to find the z that brings it as close as possible to the latent space representation of the output, and then you fix it there. And now this is the actual distance. So that's what I understand from
Yeah.
the presentation.
Mm-hmm.
nice. Yeah. Okay, now makes sense. Thank you.
Okay.
So
So
the
just
sorry,
to
one
clarify
question.
it a bit more. So if you can see on the screen. So let's say this line this whole line represents the options, or like you were representing different options of let's say there was a fork, right? You were representing two options that are possible right there. In the signal there could be multiple options, so let's say this line whole represents those options, right? Now once you go through the X encoder and the predictor the first time, what you will get is something like this. You will get a point on this line somewhere, let's say, right? You'll get a point on this line somewhere. The predictor models it like this, that you get a point somewhere here. Now, what you will do is after getting this, you will again use this. There'll be a loop right here on the predictor where you will minimize it using gradient descent, minimize the z thing, and this dot will now move closer and closer and closer towards y on the line. And then once you have minimized this will be your final distance. This will be your final energy. Is that clear?
Yeah, it
Yeah,
is good. Yeah.
that makes sense.
No, can you repeat it once more? So X goes to the encoder, and after you get the encoder output, then you minimize Z.
Yeah, so after you
So
get,
okay.
because
So one more question: what exactly is a predictor when you are implementing this a neural network?
yeah, so I've not gotten to that part yet.
Okay. So I am
What
trying to understand what Z exactly is. So if a predictor is a neural network, then it must be a some sort of parameter of that neural network, no?
I think, yeah, Z is gonna be changed, right, during training or what the process.
Yeah, so z is a latent variable.
Mm-hmm.
It
So
can
latent
take a
variable is
multiple
like
values.
it can be a hyperparameter of the neural network.
Yeah.
What type, like
uh
what?
Okay. Okay.
okay. Okay, so nobody has any other questions. So can we move forward, or is there any other questions that you want to ask?
Yeah, go
Okay.
ahead.
Okay. So now let's come to how do you train a JPA? So what you want to do is have four criterias. That is, the first thing is that you want to maximize the information content of the encoding that you will get out of the X encoder. Second is maximize the information content of the Y encoder. And you have to minimize the prediction error right there. That is there. And you have to minimize the information content of Z. Z has to be restricted. It cannot be a large Z, because if it becomes a large Z, instead of taking in just the options that is the uncertainty, it will take a lot of other informative things that could be really useful. It could take in all of those things. We need to constrict Z so that it just only contains those uncertain problems out there. Okay.
Yeah. So I
So these are,
understood it clearly when you draw the line and say you allow it to vary, like move over the line. So if you don't constrain it on the line and let it move anywhere in the 2D grid, it can just any SY can map to the uh, original, like the expected output. So
yeah,
that's one way to understand.
yeah, that's one way to understand. That's right. Okay. So uh, so how do we do all of this? So the okay, let's talk about the minimizing the information content of Z part first. So to do that, what we can do is to make Z discrete. We can use a discrete vector space and have it be discrete instead of something continuous, because continuous things could take a lot of values. Discrete can just take a bunch of values, not more than that. So you can discretize it. You can make it low dimensional. You can make it sparse, noisy, and also you can use a stochastic sample from a distribution whose entropy is maximized. This is just a sentence which is a bit more complicated. That just means use something like what is done in variational autoencoders, right? So this is how you will minimize the information content of Z. And for okay, so there is a counterintuition right here. Uh, so if we were to maximize the information capacity of encoder X and encoder Y, it can take a very large representation space. Like you just explode the information capacity by just let it be of a large representation space. You give it a very large dimensionality of to you give a very large dimensionality to encoder X and encoder Y. That is how you increase the information content, right? You increase the dimensions. So that is what you do. But we already know there's a lot of problems associated with doing that, right? Because there's a curse of dimensionality, there's a collapse happening, there's a lot of things. So what do we mean by doing maximizing the informational capacity? So what precisely what we want is that it should be maximally informative but minimally surjective. So the different, it would be like different points mapping to a single point, not very different points. So if let's say 4 points are almost the same, they belong to the same class, or they have the same structural content, they should map to a single point or something very similar. They should not be exploding out of the way. So it should be minimally surjective. So four points, if they are if they mean the same thing, they should map to a single point. That is what I mean by minimally surjective. Is it fine? Okay. Okay, now how do we convert all of this into a good enough differentiable loss? Okay, we have to convert this all of this thing into a loss function that could be applied over this. Okay, so this is where VicReg comes in. VicReg is the paper in itself. You can go through it. So I'll just introduce the concepts. The concepts is the full form of VicReg is variance, invariance, covariance regularization. So in here, what you're doing is you are, okay, let's first look at what each of these variance, invariance, covariance actually means. So VicReg is a simple non-contrastive method for training embeddings. It's a non-contrastive method. So by variance, what we mean is maintaining the standard deviation of each component of Sx and Sy above a threshold over a batch. So variance, we are calculating over a batch. So the representations that you are getting over a batch should have a standard deviation over a certain threshold. That is variance. So you're ensuring that the representations that you're getting of different points is different, has some kind of a difference. There is standard deviation. So it leads to not being collapsed to a single energy point, because if everything was to collapse to a single thing, the standard deviation will be zero, right? So you want that standard deviation of the representations to be above a certain threshold. So that is what they mean by variance. Okay. Invariance is just the representation prediction error. It's like, so you have corrupted one part of the input, you're giving the normal part above, and you're finally comparing the prediction, both of the predictions. So that is just the representation prediction error, invariance, because you have corrupted this part. So this part is becoming invariant. So that's why it's called invariance. Okay. And covariance is to drive the covariance matrix towards an identity matrix of one single representation. So one single point, you have a representation for that. For that one representation, you would construct a covariance matrix. And in that covariance matrix, you would drive that covariance matrix towards identity, so that there is no multi-collinearity between features or collinearity between features. You want the covariance matrix to be identity matrix. You will drive all of the other values in the covariance matrix towards zero. You will drive it towards zero. It will naturally not be zero finally, but you will drive it towards 0, but you will not let them be 1. That's the whole point of covariance. Is that clear?
That part is not clear to me. So, covariance of Sx and Sy, we want them to be identity matrix.
So in covariance, what you would do is, so let's come to this part now. Okay, so you have an X that goes through the encoder X. In Vicreg's paper, what they have done, they have an expander module right here, which expands the representation. And over this, you have this one representation, right? There is a, let's say, imagine you have an n-dimensional vector. That n-dimensional vector, you'll use that to create a covariance matrix, right? So a covariance matrix over that one single vector. And over that one single vector, you will calculate, you will apply a loss that would drive it towards identity matrix. Okay, so there's an expander module for that here, and there's an expander module for encoder Y also. There is a loss function right here. There's a L2 loss. Okay, so you have variance being calculated that is being over the batch. It's not over one single point. It's calculated over the batch. Invariance is the part where you are feeding the encoder X with some uh, uh, corrupted input, right? That's where invariance comes in. So variance, invariance, and then covariance is through these expander modules, and then you want this covariance to go towards an identity matrix.
Okay, so that means like when we are expanding the original representation Sx to Vx, like given one Sx, it should always produce one Vx. Like there should not be any variance, something like that.
Yeah, so it's like you don't want so if you have a n-dimensional vector, so for each dimension, you don't want these dimensions to be related to each other in any way. So you want them to represent their own thing instead of being a linear combination of each other.
Okay.
Does that make sense?
Yeah.
Yeah, it is good. Just a quick question, like it is tending towards the identity matrix. Is there
Yes.
can be some case when it is equal to the identity matrix?
I don't think it will happen that way, because
Okay.
if if it happens that it becomes equal to the identity
Mm-hmm.
matrix,
Yeah.
what does that actually mean? Like if you have an
Just the
identity
same,
matrix.
just only the diagonal. Yeah.
Yeah.
Okay.
So I don't think that can happen because of the L2 loss that you're using with that, because you're trying to make two representations equal, and I don't think that can happen, because to get a covariance matrix that is identity, that would mean that it's completely uncorrelated. Might happen. I don't know. I'll have to look into it. I'm
Yeah,
not
I'm
sure.
not sure, but I'm curious about like what will happen. Yeah, that's okay. We're good.
Yeah. Yeah,
Yeah, got the
maybe
idea.
if you go through the Vikreg paper, you can answer this
Mm-hmm.
question.
Maybe. Yeah. Yeah, I'll
Yeah, I
go
have not
through
gone
that.
through the paper, so I don't know.
Mm-hmm. Yeah, good. Yeah, got it.
Okay. Any other question?
No, thank you.
Okay. So one thing to keep in mind is when you're reading papers which have used Vikreg, that Vikreg is contrastive over components. It's not contrastive over vectors. It's a regularized method. It's not a contrastive method. Okay? Because sometimes papers will mention it like a contrastive thing. It's not a contrastive thing. Okay. So coming to this it's like the last part. There's not many things left. So there is something called hierarchical JPA. So in hierarchical JPA, what you do is it's like um, so let me give you an example. Is there a pen? Okay. So let's say your car was right here and there were different cars on the way. And one right here. So when you are doing some kind of thing in hierarchical, you're building some kind of a hierarchical model, what can happen in this way is your actual trajectory would be something like this, like different. Your trajectory of your car will be something like this. You'll be going around cars and doing some kind of lane switching and all. So there'll be a different trajectory, different weird kind of a trajectory right there. So when you have a hierarchical model like this, what you can do is uh, having uh, a JPA that is on the lower side, it can give you a, a representation for just this part that is more granular in nature, because you are uh, adding that um, predictor network and everything on the initial few layers of the encoder, of the X encoder. So if you have a X encoder and a Y encoder, so if you're just doing it in on the first few initial layers, we know that it does something very granular in nature. Like there's a lot of information about the whole input itself, right? So in the lower part of the hierarchical JPA, you would get local information and you can make predictions in the localized thing. So eh, in this example, what this could do is that you can model this part, just the trajectory of of a few seconds of your trajectory. You can model that with the lower level representations. But if you were to go into more abstract level informations, like if you were to add a hierarchy on top of that and make it more abstract, what you could do is make long-term predictions. So you would get something like this curve, which will tell you, okay, this was your trajectory. Instead of, you'll get a whole picture and an abstract representation instead of a granular representation. So granular representation would be constructed to a local window, and um, a more abstract representation could give you a long period analysis. Okay, does that make sense? Okay, so one more thing that I want to add here is, it is very important to note that the generative latent variable models that we saw, the generative models with a latent variable, they are not capable of eliminating irrelevant details, that is abstracting, other than pushing them into a latent variable. Okay? They are not capable unless they have a latent variable. Even with the latent variable, they have a very limited space of doing that. But in JPA, you are doing that in representation space, so you have the there are two things there that are doing this for you now, because in representation space you have abstracted away the information, and with Z you are managing the uncertainty. Is that good? And if you see so if you go through the paper of Dino, so the first paper of Dino, if you go through that, what they had done was, they had trained their whole this form of an architecture. Let me show the architecture again. Yeah, so they had trained this form of an architecture, this one. So what they observed was that if they introduce a class token in this encoder, a class token can be considered as a latent variable, right? So when they introduced a class token, they observed that the okay, let me go back first. Okay, so without the class token, they observed there was a lot of different information that was being carried by the encoder inside the representations, different representations, because they were extracting the final attention maps out of it and looking at the attention maps and seeing what's there. There were some granular things out there. In the whole image, there will be some pixels highlighting just randomly, and there will be some information there. So they observed that there is something weird going on here, and once they added a class token on just the encoder part, what happened was these granular things disappeared to a large extent. So what they finally came to the conclusion was, with the latent variable, what happened was these extra information that the model needs to carry gets into the latent variable. So in their case, it got into the class variable. So class variable, when they say a class variable, it's not just a 0 or 1. It's a huge vector. So that is what actually happened in Dino, and they saw that it's happening. So it does happen. Okay, so this is what I wanted to highlight, which I got to know right now. And after this, so okay, so um, I think we are at a point that we could decide if we want to look at IJPA again. Like, I think Daya, Udavaya, and a few others have looked at IJPA and all, IJPA and VJPA. I just have these things left. So do you want to go into this, or is it enough right now? Because I know it can be a lot to take in one go. So is everybody on board? Or do you want to continue, or do you want to make this into a new session any other time? Yes, no.
I think this is fine. If someone wants to continue, that's good. But you can go ahead with it then in some other section, like session as
Okay.
well.
Yeah, I
Just
mean,
gi
I
just give
Yeah,
me
would
a
that's my
also
feeling too.
say
Yeah.
that, okay, because like we have to take in all the basics and then understand the IJ power, and that would be
yeah.
good if we can schedule another session on this thing.
Okay, okay. Just give me a second.